Finally, our last video on amino acid structures. My tongue is very tired at this point because it seems like that's all that we've talked about is these R groups and how to name them and the three-letter and the one-letter abbreviations. And we've spent, now 10 videos on talking about the structures of the basic building blocks for proteins. And we've got three left. And these three represent the family of heterocyclic amino acids. And heterocyclic, hetero means different, right? You're heterosexual, well, different sexes, different opposite sexes attract. So heterocyclic means there's different things in the ring. So when we talk about a ring for the R group, it's not just a carbon ring that's involved. There's some other things that are there that are going to make themselves known. Now, nitrogen is very common, found in a ring. Our carbohydrates were heterocyclic rings, right? We had a carbon ring, but one of those locations was an oxygen that connected the ring together. So we saw heterocyclic rings in carbohydrates. We're going to see heterocyclic rings in the amino acids as well. There's really hardly any difference in why and how. So let's take a look at our first one. And this first one is a CH2 group. And off of this CH2 group, we are going to get a five-membered ring. So 1, 2, 3, 4, and 5. So yeah, I'm horrible at drawing the rings, but there we go. So there's 5 rings. On this carbon, well, we've got a double bond, and then there's a carbon. This, though, is not really a carbon. This location, it's a heterocyclic ring, right? So this is going to be a nitrogen at that spot. And then we see another double bond here. This is a carbon. And then that's connected to that spot, but that's not a carbon either. This is also a nitrogen. And this nitrogen's different. So this nitrogen wants 3 bonds in total, so that means we have to give it a hydrogen to make the neutral charge or make the formal charge of 0. So this carbon has 4 total bonds. This carbon has 4 total bonds, one of them to a hydrogen. It's not drawn, but it's understood to be there. This nitrogen has a total of 3 bonds. This carbon has a total of 4, one to a hydrogen that's not drawn. And this nitrogen has a total of 3 bonds. So they're all happy. And when we look at this CH2 with a 5-membered ring, this structure is called histidine. 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 Histidine, 3-letter abbreviation is HIS, and 1-letter abbreviation is H. So histidine. This is not histamine. For those of you with allergies, you are very familiar with histamine. This is not histamine. That is something completely different. Histidine is an amino acid. Histamine is not. So one of those things where a slight ending change really gives rise to a completely different type of molecule that does a completely different type of job. So histidine, there's the structure. Okay, so heterocyclic ring, right? It's a ring, but it's not all carbons. There's other things besides carbons that are in that ring. Okay, so there's our first heterocyclic amino acid. Okay, what about our second heterocyclic amino acid? Well, this is a CH2 group. And off of this CH2 group is going to be another 5-membered ring. You can draw the 5-membered ring however you wish. It doesn't really matter as long as it's 5 members. It's all that we're after. But off of this 5-membered ring, we also have a 6-membered ring that kind of shares the side to it. So now we're really testing your artistic abilities. Art 101, thank you for allowing me to take you as an elective, right? Because look at what has happened. Art 101 has prepared me for organic chemistry. As you can tell, I didn't probably do too well in Art 101 either. So this ring is a benzene ring. So I can go ahead and draw the circle in there if I want. If I don't really like the circle, then I can do the alternating single and double bonds. If I want to do that, that's okay. There's a double bond here that's shared between these two rings. So it's double, single, double, single, double. So if that's what I like to see, I could do that as well. I don't really like to do that though. That bothers me. I don't really like to see that. I like to draw benzene and its delocalized structure, and there we go. Off of this carbon, we see a double bond that's here. And then down here at the bottom of this ring, we actually see a nitrogen group, and that right now only has 2 bonds, so we have to throw in a hydrogen to make a formal charge of 0. So there is our second heterocyclic amino acid. Notice these structures are a little more difficult to draw, right? And this is what we call tryptophan, Tryptophan, tryptophan. Tryptophan's 3-letter abbreviation is TRP, and then the 1-letter abbreviation is W. How do I remember that tryptophan is a 1-letter abbreviation of W? Well, look, if I can draw the structure for tryptophan, I can kind of make a W out of this structure, right? I can kind of see the W there, and that's actually how I learned how to draw tryptophan. So I remembered tryptophan, I knew the 3-letter abbreviation was TRP, and then I knew the 1-letter abbreviation was a W. So that's how I started off the structure. I drew the foundation, I put my CH2 there, that's the connector link, and then I just kind of drawn the W on. So that seemed to work out well for me. You just kind of got to block it out in a way. And then when you do that, you can just kind of go ahead and connect the rings on around, and you basically have the structure for tryptophan. So that was kind of a nice little trick that I did to memorize this structure. It seemed difficult to me when I was taking organic the first time or biochemistry the first time, and that's the way that I kind of remembered it to help me along. Okay, so we've got one more amino acid left. And this amino acid is also another heterocyclic ring. Now I'm saving this to last because this is kind of a weird one. And what happens is that the group kind of swings around on itself. So what we have is a R group, and this R group is a CH2 group. And when the CH2 group comes around, it's going to be connected to another CH2 group, and then that's going to be connected to another CH2 group, and then that's going to be connected to another CH2 group, and then it actually swings around on itself, and it connects up to the NH3 group that's up at the amino acid at the top. And when this happens, well, this positive goes away and one of these hydrogens disappear, and we get a NH2, but I'm sorry, that positive is still there because that nitrogen still has 4 bonds. So we get this kind of structure that begins to happen. And this is our really only amino acid that hooks back around on itself. So we get this long kind of floppy carbon chain, and this long floppy carbon chain swings around and it hooks up with the nitrogen and it forms this ring, a heterocyclic ring. But the difference is that the amino group of the amino acid is actually part of the ring, and we've got the nitrogen there because of that. Well, if you don't like the way this looks, because I know that it looks kind of messy, we can kind of simplify this down a little bit if I don't want to draw all of those carbons there. So we said 5 carbons in total, right? So 1 or 5-membered ring in total. So we see a 1, 2, 3, and 4. So I can do that if I want. That's okay too. That doesn't really matter to me. However you want to draw it, it doesn't matter. So there we go. There is our structure for proline. And proline is Proline. and 3-letter abbreviation is PRO, and a 1-letter abbreviation is P. And I actually made a mistake in this structure. There should be only 4 carbons in total with this ring structure, this being one of them. So this is my first carbon, and we need to do a second carbon, a third carbon, a fourth carbon, and then finally the NH2 group. So let me come down here and draw proline maybe a little bit better for you. COO minus, and this COO minus basically has a carbon, and this carbon can go up and then out and then down, and then the nitrogen, which has an NH2 and a positive on it, and then it swings around. So this is our structure for proline. So just to clarify it up a little bit, there's the structure for proline. It's 4 carbons in the ring with nitrogen. So 1, there's the alpha carbon, 2, 3, and 4, and then nitrogen makes the 5th part of the ring for the heterocyclic ring itself. So there's histidine, tryptophan, and proline. Notice all of these amino acids are called by their common names, and the common names are basically what we always go by. We can IUPAC them if we want to, but we will not IUPAC the actual amino acid structures. They all come from, they're not made up, they all come from some kind of history with the amino acid. For instance, glycine got its name because it's very sweet. So glycos is the old Greek term that means sweet. So that's where these names come from. Valine, well, you should go back and you should remember carboxylic acid nomenclature, carbonyl nomenclature in general. A 5-carbon ring was called valere. So we see 5 carbons in total for valine. So there's a rhyme and a reason for these names of amino acids. They're just not made up. Asparagine, well, asparagine was found in asparagus, so that's why they name it asparagine. They kind of give respect to the origin of the amino acid and where it was first discovered. Tyrosine, isolated from cheese. So tyros is Greek for the word cheese. So very, very systematic nomenclature in place. If you just go back and take a look at where the root word comes from and why they have decided to name it the way that they have. So it's just not made up out of thin air. There's actually a purpose to it. So you can go back and do a little bit of research if you want, but that's where these names are coming from. So IUPACs do exist, but we call them with their common names most of the time. So this sums up the amino acid structures that you need to know. There are 20 of them. You need to know all 20. There are 20 names that you have to spell correctly. There are 20 3-letter prefixes or abbreviations that you have to know, and there's 20 1-letter abbreviations that you have to know. So I would take some time, go through, make sure you memorize all of these, because this will be a very big point value on the upcoming amino acid test. Don't let wasted points throw you off. Know these amino acid structures, and you should at least score halfway decent on the exam itself.